All right, so and it will be me will be upside down in here, okay, because the camera is right in front of me. Wish we had a different way of doing things. Okay, so the vacuum means this. I'm looking at this point, and at that point there is no electric current density or no electric charge density. So when we write the Maxwell's laws, Maxwell's equations, we just set them to zero. So one of these Gauss's law used to be rho over epsilon naught, okay? So this is zero. This used to be rho over epsilon naught, okay? If you look up in the book, you will see rho epsilon naught, right? And then you had, so I'm not gonna start writing, I'm just gonna forget all of those things. I'm just gonna write full laws. And another one is gonna look like del dot B equal to zero. This one everybody knows that, right? This is means no magnetic monopoles. That law means no magnetic monopoles. And then there is a Faraday law, right? This one is called Faraday law. So you might say this one is like Coulomb, comes from Coulomb, and this is no magnetic moment, magnetic monopole, not moment, monopole. It's like there's no such thing as the North Pole only. There is no such thing, okay? I mean, if you find something like that, you're gonna get a Nobel Prize for it, all right? Because this is built into the system. I mean, this is wrong. If anyone can discover a single North Pole type of object, wow, power to you, okay? And this one is Faraday law. That one, this is written in derivative form, right? And you've probably seen in the integral form Faraday law. You've seen like EMF is this, that, right? EMF is change in magnetic flux, right? You've seen that, right? Rate at which magnetic flux changes is the induced EMF, right? That's what this law is. How many of you know Faraday law? Okay, I got it, okay? Yeah, actually Faraday law is a very cool thing. You can see that electric field will produce magnetic field, and changing in a magnetic field, you don't need any charge. It's saying you don't need any charge to produce electric field. All you have to do is swing around magnetic field. So while you are changing the magnetic field, you are producing electric field. That's just cool. And then there is an Ampere's law. This is Ampere's law. Ampere's law had a current on the right side, remember? Del cross B, you had a current on the right side, mu naught J. But instead of that, J is 0, so J is 0, so I'm going to have a mu naught epsilon naught. This is what Maxwell found. This term was missing. Experimentalist has missed this term. I'll show you why this term is easy to miss, okay? But this is a correction course. That's what we call a Ampere Maxwell. So Ampere's law, but this is Maxwell correction. So just maybe should recognize Maxwell. This is the thing that Maxwell actually found. You will see that mu naught epsilon naught is actually 1 over speed squared. You will see that if you just multiply those numbers, you will come out to be a speed of light in vacuum squared like that. All right. And now you can see why this one will miss it. If I just use that, I will see 1 over c square dE dt. Now you see this term will be missing, right? So over here used to be plus mu naught J. This is the actual current, okay? If there was a current through that point, all right, then I'll have that term also. So I'll have two terms in the actual law, this term and this term. So can you see why this term, you are an experimentalist, you would miss this term? Tell me why I would miss this term.
Because it's so small.
Yeah, it's really small.
Yeah, it's tiny, right? C square is like humongous, right? I have to vary this guy very fast, right? I have to change electric field very rapidly in order for me to see this thing, right? That's why I missed it, and we had to do experiment at very high frequency to discover this presence. You know, so it was missed for a long time, almost, you know, you would say Faraday Law, Ampere's law was found in 1830s, okay, and they didn't discover this term till 1880s. It's almost 50 years people had missed this. It was there, not for lack of trying. It was very exciting time, 1800s, okay. 1890 was a very hot topic then. So this is not there, so we have these guys, right? So now you can go through the exercises and you'll see that if I do this equation, okay, I say I'll do del cross on both sides. All right, I'll do del cross on both sides. So what I'm going to get on the right side, I'm going to get minus del cross dB dt, right? What is del? Del is, in Cartesian, will be I hat d dx plus j hat d dy plus k hat d dz in Cartesian, right? You can write this in other coordinate system. Everyone has Calc 3, right? You guys all either were in Calc 3 or completed Calc 3.
Or
Yeah. So this is kind of, let me write this down, little joke here. Attack of Calc 3. It may be for some people worse than coronavirus, okay? You know, this Calc 3 is very important part of your calculus. You know, if you have not done well in Calc 3, you better go back and redo Calc 3 very well, because you are going to need it, okay? All right, so you have a derivative, right? And this is an operator. You have a derivative. This is another time derivative, right? So derivative will go inside. So if you look at inside, there will be things like d dx, d dt, right? Type of terms, right? So I can write down d dt, d dx. There's no reason I can't write that. The linear operator. So this one I can write down is minus d dt del cross d. The reason I want to write down is I can use this guy in here. So when I do that, I get an equation only in electric field, right? So that's going to be minus d dt mu naught epsilon naught dE dt. These guys are universal constants, right? They're just constants. They are the properties of vacuum, and vacuum is, you know, universal. It's giving universal constant, so it's going to be minus mu naught epsilon naught d square E dt square. So what we found is del cross E is that.
Right.
Well, this looks nothing like wave equation, right? Except that when I do left side I do again, I do Calc 3 here once again. All right, for those of you who've done Calc 3 or in Calc 3, you should try this, okay? You can show this is del of del dot E minus del square of E. I think this is correct, okay? I hope I'm correct because I'm using my memory. I'm not proving it on spot. What I'll do is I'll expand this, right? Some of you know how to expand this. I would expand this. You know, del dot of E is dx, not shorthand ddx. ddx can be written as dx, okay? Ex plus dy ey plus dz ez. But del cross of E turns out to be, you can have a I hat, j hat, k hat, dx, dy, dz, ex, ey, ez. So these are the components of electric field, right? And this is the determinant you work out, right? You know this thing, right? So you work out the determinant, and this is a vector. So for instance, its x component, del cross E, x component will be dy ez minus dz dy. Alright, so you can work out that, and then you expand the hell out and you get something like that. Well, guess what? I'm in vacuum, so this guy is 0. So this equation for me in vacuum turns out to be minus del square E equals to minus mu naught epsilon naught d square E dt square. Now looking like the wave equation, right? The minus got cancelled out. So if this was some kind of 1 over speed square, it will be wave equation in 3 dimension. I didn't say what del square is. Del square is d square dx square plus d square dy square plus d square dz square. So it's a shorthand notation, and it's called Laplacian operator. And I'm writing this in Cartesian, so if you are working in some other coordinate system, you'll have other forms, all right? Much more complicated forms. All of these, when you get to the physics 482, okay, electricity and magnetism, something to look forward to, okay? All of this will be in that course in a very big detail. Lots of problem, lot of practice you're gonna have there. All right, something to look forward to. This course is all about this, doing this kind of stuff. Okay, so we have a del square E equals to 1 over c square. I'm going to call this 1 over c square and d square E dt square. And so that's what we got. Okay, then you say, well, how about the magnetic field? Well, when you go back and do suppose you attack this equation, you attack this equation with del cross and you manipulate all kinds of same way, guess what? You're gonna get a same equation for B also. Del square B will be exactly same equation. So you get that. Okay, I didn't write that, but you should do that exactly same way. It's gonna work out. All right. But this is not enough. They have not only they obey this, they have to obey all the other equations, right? So they have to obey del dot E equal to 0. They have to obey del dot B equal to 0. They have to obey del cross E equals to minus dB dt. And they have to obey del cross B equals to mu naught epsilon naught dE dt. They have to obey all of this, okay? So electric field and magnetic field have to obey all of the 6 equations. Now you see, like, oh my God, where the hell? Light is so simple. Why are you complicating it, right? It's actually very complicated. Light is uh, yeah, light is a pretty complicated stuff, you know.
Yes, sir.
So you have to obey all of this, okay? All right, so it seems like a hopeless task to do. Best is to start some simple situation, right? So let's see, we're gonna do just solve this guy first and try to force it to obey these guys, all right? You know, so we'll try to force it to obey these guys. So we just solve that. So what is we're going to look at some called harmonic solution. Harmonic traveling wave. You can also study easily harmonic. Tell me what other kind of thing I can study. I can study this harmonic traveling wave. So what's another kind of study I can do that's easy to study of waves? It would have to be harmonic, right? So instead of traveling, I can do standing waves, right?
Yeah.
Harmonic standing wave. So this will be the case, for instance, in laser. This is what you do in laser, right? Inside the laser. Inside the laser. I'm not doing traveling, okay? Inside the laser is bouncing back and forth, right? You know what I'm saying? You got a box and this thing is going back and forth. It's kind of like a string, right?
Yeah.
It's going back and forth. So you're gonna have to disappear here and disappear here, right? So it's gonna have to be fit, so to say. It has to fit in here. You know what I'm saying?
Yeah.
So these are standing waves. Another example is like in an oven. So this is a closed oven. You've probably seen that in a closed oven. At some temperature T, inside is basically heat, right? Inside is heat. What is heat? It's actually electromagnetic wave. Heat is nothing but electromagnetic wave. I bet you didn't think about that. Well, what kind of wave will it be? Will it be traveling wave? Well, you have finite boundary conditions. Whenever you have finite boundary conditions, okay, you have finite boundary conditions, it's going to be a standing wave. The dimension in which you see the finite boundary condition is going to have it has to be a standing wave, because it's going to go back, bounce back and forth. So you're going to have a wave going to the right and wave going to the left, a wave going to the top, another wave coming back. So you're going to have a mixture of two waves in the direction that's finite. It's a very important point to notice, all right? They're related to each other, right? I can always write a standing wave as a, say, if I have a standing wave to the right and left, I can have a traveling wave to the right plus a wave traveling to the left. That's the trick. So they're not like two different things, but here frequencies will all be discrete. So they're all discrete frequencies. That's what we get from standing, because you only can fit, Over here you get continuous frequencies. So, but single frequency. Harmonic means you got single frequency. That's what harmonic means. You got single frequency. And the way we know it is because the wave can be described as a cosine or a sine. Right? Okay, so I do harmonic traveling waves. We're going to do this. So, which means let's look at a electric field as electric field at some point x, y, z at t. So I want to guess what the answer will be. It will be some amplitude, which will be a vector, and then I'll have a cosine kx along x plus ky along y plus kz along z minus omega t. And then there is a phase constant, okay? If I have a single wave, I don't care about the wave phase constant. But here we have three different waves, so I'll have phase constant will be kind of like a vector, okay? So there are three waves here. So let's see if I had a x component, so I'll write a phi x, and then if I have y component, then I'll have another amplitude with some kind of constant field, and cosine same plus phi y, kx all the way to there phi y. So because we'll have three waves, right? So we're gonna have to have this will be same plus phi z. So the phase constants, go with each wave. And so if I was writing earlier with a vector, I couldn't write as a vector here because these are all scalars, so I can't write a vector down there. You know that, right? That's why I couldn't write that. I had to rewrite this thing as a components. Because each of the components is each one of the waves. Well, so if I plug this back in here, let me see, plug this back in here, it won't surprise you that I'm going to get kx square plus ky square plus kz square equals omega square over c square. This is a dispersion equation. It's called dispersion equation for EM wave in vacuum. We're doing vacuum, right? If I was doing some kind of material, then this will be the speed in that material, right? You know what I'm saying? If I were doing something in material, this is speed in that material, and that speed in a material may depend on the frequency of light and may depend on the these components, right? And so it would be complicated, and that is what you learn when you do electricity and magnetism so okay, so we got this. This is what you got. So we can say k, this thing is nothing but magnitude of k square equals omega square over c square. So this will be everything is positive, omega is positive. We can do like this, k equals k times c, kc equals omega. Sounds right, okay? Or you might say, yeah, omega over k, it's the same thing as before.
Cool.
It's the same stuff, right? So this is telling me what the phase velocity is, right? So is c. So c is the phase velocity, all right?
Right.
You can say that if I had a weird material, that c can be more than speed of light. We already talked about group velocity is the velocity at which the information travels, not at this velocity, okay? This can be whatever it wants. So there are materials you can find omega over k, say c material, that can be c vacuum, allowed, okay? This is allowed.
Interesting.
This is not like, oh yeah, my god, I violated the Einstein's speed of light problem, okay? No, you don't violate speed of light problem. This is omega over k. It's not group velocity, right? So I'm not going to go more along that direction, but once you say the omega k is just a c is something appeared in our equations, right? And that we are saying it is at which this phase of this thing moves, right? It's the phase velocity. It's not at which the energy will move. All right, but if I had just one wave like that and in vacuum, it is the speed at which energy will also be transported. So right now I'm not violating anything, okay? I'm just saying if I was if I was in a material, okay, I could get larger than the speed of light. That makes no difference to me, okay? As a physicist, I'm not alarmed, right? Okay, so let's see. We also know that k is the wave number, and so 2 pi over k will be number of waves, length over which the wave number is. So this is the wavelength. This is the same thing that you learned before, and we can use letter lambda for it. I guess let me see if I can switch to a more fast presentation. So if I can stop share, go there, share screen, my notebook, okay, and I go to the notebook, wave, the notebook. Okay, so I am going to be really fast now. So we've done the harmonic wave, like I wrote earlier in terms of exponential rather than cosine. It's the same thing, okay? So I have 3 of these guys, okay, and we've done this so far, emerge. Now if you say del dot E, so this comes from del square E is d square E dt square 1 over c square. So it told me that, but this has to also obey del dot E equal to 0, right? So if you look at del dot E equal to 0, you get this. What do you think it tells me? I got 3 waves, right? They're not all independent of each other. There are only 2 of them independent of each other. Because if you give me like these 2, I can get that, right? So if they're not independent already, I already see the problem here, right? So I'm going to say, all right, traveling, let's look at an example of this. Say I'm going to look at a wave that's traveling towards the plus z axis. Well, you remember k in our wave is also propagation vector, right? The direction of this guy tells me the direction of propagation, right? So if something is going along the x-axis, you had a cosine kx minus omega t. So what does it look like? This is cosine k sub x minus omega t. That's what this is, the direction, right? The direction of the k vector. Direction of the k vector tells me which direction it's going. It's going towards the x-axis, right? So this k vector is very important. It tells me which way the wave is going. So if I want to look at z-axis, that will be the non-zero, and these guys will be 0. Then if I plug in there, I get k times, so this gives me k e sub 0 z equal to 0. Of course, this wave, this guy is 0, this guy is 0, but this guy not. So k can't be 0, otherwise it's not a wave, right? So k is not 0. Then I see that if something is going along the z-axis, can't have E0Z. I don't even have to find E0Z. E0Z already 0. So if the wave is going along the z-axis, the electric field can be in this direction, in this plane, okay, in the xy plane. So we say the electromagnetic wave is a transverse wave. It's going along the z-axis, then it can be pointed only along the axis, plane perpendicular to it. You might say, hey, that was like, you pick a z-axis, that probably killed a lot of terms, and maybe it's unfair. You should prove it generally, right? You not just say, oh, z-axis. How about if we're going in a random direction? So you may want to prove this yourself. So I picked up a random direction, okay? So if I go in that random direction, that's the wave going in that direction. I need to prove that electric field will be pointed in this plane, right? Correct? So these will be the magnitude. These are the values of electric field. Those are constant multiplying it, right? Those are amplitude values for three waves, right? So electric field will be at some point at some time will be just equal to E0x I hat plus E0y j hat plus E0z k hat. So this point is assumed so that cosine of this whole thing is equal to 1, okay? And this is k dot r minus omega t plus phi. So I assume that there is a time and a place where this is equal to 1, okay? Then these guys just add up like that, right? So that's where the electric field is pointed. And maybe that's pointed in that direction at that point. That can be in this plane. I need to prove that it's in this plane, right? And guess what? When I do, this is k dot e equal to 0 gives me this. This is just basically tells you equation of this plane that this guy has to be in. This point has to be in this plane perpendicular to 2, 3, 4. So it's not just for z-axis, it's for whatever direction you want, Okay, so having proved that this is always transverse wave, electromagnetic wave in vacuum is a transverse wave. I didn't prove that electromagnetic wave in a crystal is a transverse wave. Okay, I'm just working out in vacuum, okay? So when traveling in a vacuum, a lot of people make a mistake, many students, they memorize this and they say, hey, when they go out and study crystal, they totally get bombed because this is not true in crystal anymore. And that's one of the interesting part of the crystal, that this thing is not true. All right? And then that means question arises, hey, which way is the wave? What kind of polarization is in the crystal, right? Which way the wave is pointed? I will say the book has a little bit more example of this, and maybe I will be able to post this online. I've been recording right now, so maybe this page is there. So I took an example of, I see already I have an x pointed this way and the y pointed that way. So this is a little different than the earlier xy directions, okay? So if I took a electric field along the z-axis, so this one an example, worked out example for electric field along the y-axis. So I took this as an example. I wave this black line going down like that. I want to know what the magnetic field will look like. And it turns out, well, I can take one of the, so this is the Faraday Law. So I use Faraday Law, so I have a right side and left side, and this I know, and I work it out, and guess what? This is what the magnetic field looks like. So if this is along this direction, magnetic field is pointed along the minus x direction. So whenever the electric field is pointed in the positive y direction, magnetic field is pointed along the negative x direction. And magnetic field is actually electric field divided by the speed of light. That's the magnitude, and because this component I have a negative sign here. But in terms of other guys are zero, so if I look at what the magnetic field is electric field over C. That's pretty cool actually, you know. This is something you should remember. This is coming from Faraday law, right? This is like fundamental law. This is always true, going to be for harmonic waves. It's going to be always true. Even if you go in whatever, right? It's going to be always true because of its origin is just I'm using a simple Faraday law. It's straightforward. Okay, so let me. I think I'm gonna go a little over. I want to introduce. In the next lecture, I want to talk about how do you take into account energy in the wave. What's the intensity of the wave? All right. And maybe on Friday when I post online, I'm going to go intensity. But let's go over a little bit. I hope it's okay. And let's talk about some of the things that we originally wanted to address, why we were doing three-dimensional wave and why we picked electromagnetic wave. This is the reason I picked electromagnetic wave. I didn't pick sound wave or matter wave because polarization is very easy to very important part of electromagnetic wave, and it is a property that you can study in electromagnetic wave more readily. It's not like this is the only polarized wave. Sound waves are also polarized if they are in solid, but much more complicated. Matter waves are also polarized if you think about the spin of the particle. All right, so things are polarized everywhere, but electromagnetic wave polarization is easier to study. All right, so we saw magnetic field and electric field are related, right? And there's much more discussion in the book about how they're related, and I would really recommend you study it. By convention, we could have picked either of them, but physicists have picked up electric field direction as polarization. That's our convention. We could have said magnetic field direction polarization, but once you know electric field direction, you know magnetic field direction, and vice versa. All right. So so if the electric field is this way, and the wave is going this way, so if the electric field is that way, then magnetic field has to be that way, and that's called right-hand rule. Okay. So it's kind of like E cross B is in that way. Wave goes into E cross B direction. So picking a direction for us has been just a convention, all right? And the negative side effect of focusing on just the electric field has been that many students they don't realize that there is a magnetic field also there. They just think electromagnetic wave is electric field. No, there is a magnetic effect, and you can make use of it. And lots of antennas, you know, use magnetic field effects rather than electric field effect. Okay. So, so this is the whatever the direction is. If the direction is y-axis, then I'll say it's y direction polarized in the y-axis. So here is a couple of different kinds of polarization that we use in application. Polarization is completely general, okay? For a physicist, it's just electric field direction polarization. But when you're applying, making a wave or a particular polarization, certain polarizations are easy to make because we have crystals to make them. We know how to make exact type of polarization. For instance, if I have an antenna, okay, it's linear antenna, and I'm passing current back and forth, okay, then we know exactly what kind of wave, what kind of polarization the wave will result, all right? Because we know that we study two types of polarization more completely than other types of polarizations. Don't mistake it like that's the only type of polarization possible, all right? That's actually what people kind of take away, and that's I regret that. But for us, polarization is just electric field direction, and for engineers and other people and lab people, they have to really focus on particular types of polarization. Even theoreticians, when working out calculations, they will usually work with plane polarization, all right? Because that's easy to do. So plane polarization is what? See, here is the wave going. If you look at you can't see my finger and things like that, and that's the problem with this, because I'm pointing with my finger and you don't know where my finger is pointed, right? This is not the way to learn, all right? This is not a replacement of in-live lecture, all right? You guys should definitely demand we should do we should demand from the coronavirus to go away. Leave us alone. That's what we demand. Okay, so here, so you can see the electric field is in this plane, right, all the time, in the YZ plane. Right, actually it's along the Y direction for this wave that I drew. And I was going to show, you know, when I put a Polaroid, this is a Polaroid. Polaroid has a, they found really nice manufacturing technology in which they can make a very thin wires, parallel wires, and they made a conductive iodine, you know, in plastic. This technology, you know, and when the electric field comes in, electric field can cause the electron to have electric force on them through Coulomb's law, right? So if electric field is oscillating, I mean changing in time, then those, what do you think the electrons in the iodine will become? They will be accelerating up and down, right? Do you know what I'm saying? It's going to be just like a cosine back and forth. It's going to be harmonic oscillator here again, okay? Remember first week we talked about that harmonic oscillator is our model. So electrons in here, they are going to be little tiny harmonic oscillators when this polarized wave hits it. And when they're doing harmonic oscillator, by the way, I'm waving up and down my hand. So when I'm doing up and down like this, okay, I shouldn't be doing that over there. So it's harmonic. This wave is going. This electron going up and down. Acceleration. You will learn sometimes. Maybe you will already know. If not, just definitely study this. That far away from the accelerating charge, you will see radiating field. You will see electric field radiated, and this is like a retarded time, you know. And this distance is going to goes 1/r. So electric field kind of this sends out electric field, and if you have plane polarized like this, and the lines are oriented the same way polarization, you're going to get your field back, okay? You're going to get your wave back. That's why the wave more or less goes through this polarization. But if I have polarized electric field like that, it hits an electron in this case. The lines are not in the direction of electric field, right? So electric field wants to accelerate that way, but there is nowhere to accelerate. The electron is just stuck. It can't jump from that wire onto the plastic is doing no harmonic oscillator here, okay, no harmonic oscillator there, then over here on the other side there will be no wave. So now you know that if I have a polarizer oriented this way, I'm going to get wave, and if I have polarizer oriented this way, I'm going to get no wave. And that's how the wave gets blocked in a simple polarizer like this, all right? I bet some of you already knew it, but some of you didn't know it. This part is a little calculation of, you know, I have this much force on the electron, this much force on the electron, I have mass of the electron, so that must be the acceleration of the electron, right? And this acceleration will go into that and give me this. Okay. All right. So we did for the y-axis. If I had polarized some other direction, the wave is still going in that direction. So these are all polarized. Okay. This polarized means instead of plane being that way, plane is that way. Plane of polarization is that way. Plane of polarization is that plane. It doesn't have to be YZ plane. It can be any direction in XY. So if I look in the XY, if I look in the XY plane, it can be any direction. So electric field will be going back and forth like that. So that will be the direction. This will be along with the z-axis. So this will go in the z-axis direction. Okay, so that's the plane of polarization, right? That's the plane we're talking about. The wave is coming out like that, you know. Okay. There is another kind of polarization called very weird. If I look at say at z1, at some coordinate z1, I see it this way. A little bit later on, I see it that way. The direction changed. A little bit later on, I see it that way. So if I look from this direction, right? If I look from this direction, what do I see? I see something like this. It used to be this way. It's kind of rotating counterclockwise, right? So this is another kind of polarization, easy to make, by the way, in the lab. This is made by what is called retardation plates. You take a light like this and do retardation plate. So this is also technology. We found crystals which do this, all right? So we use very thin crystals of some kind, and you can study more, and then we kind of slow, say, x component compared to the y component, all right? So we slow a little bit, one wave from the other wave, and then what we find is we made this kind of, the light is coming in the z direction, but in the xy plane, the electric field is not maintaining its orientation, you know, in a plane. It's actually rotating around. So this is very useful, actually. This is called, I like to call it counterclockwise rotation because it makes sense to me. So if I'm looking from here, it's look counterclockwise. If I look from the back, it's going to look clockwise, right? Right. But it's also called right circularly polarized. Why is it called right circular polarized? Well, look at right-handed rule. So if you put your palm and rotate, your thumb will be that way, right? Your thumb is pointing towards where the wave is going. But you got to be looking at it, right? As the wave coming at you. You know what I'm saying? It's kind of looking at it as a wave coming at you. All right, so there is, it doesn't have to be circular. It can be elliptical. It doesn't have to be elliptical with your choice of axis. It can be just random elliptical, some angle. and so there will be some kind of relations between x and y components. If circular, they have to be like rotating in a circle, right? Electric field x component, y component just be random, they're falling on a circle. And same here, x and y component can't be just random, there has to be falling on an ellipse. I think I don't want to talk more on it. I see already I'm going to have to put up a video on the polarization by separately. We already talked, I've recorded 50 minutes already, okay? And I want to stop here. I'm sure you have other things to do, right? There are other classes, right?
Yeah.
Did you miss any class right now?
Oh, heck no. No. But I feel so.
I'm glad that
I
you
got
missed
a call
so
soon.
much. I'm going to post this polarization direction because actually it's too much to absorb in one lecture, We'll see how this video came out. I'll play it out. If it didn't come out right, then I'm going to record again. It's called take 2 in the video recording industry. All right. Really nice to see you.
Bye.